Good morning, this is Naresh, working as assistant professor in EC department. Today we are going to discuss the question bank discussion on module 1, that is diode applications. So in this session we are going to discuss some brief discussion about the question bank problem sizes of the article questions on diode applications. So in the first, the question is compute the value of DC resistance and AC resistance of a germanium junction diode at 25 degrees centigrade with I0 is 25 microamperes and at an applied voltage of 0.2 volts across the diode. So here they given that the temperature is 25 degrees centigrade and I0 means reverse saturation current. The voltage across the diode is 0.2 volts. Now we need to calculate DC resistance and AC resistance. So for this case, so based on the diode applications, we know that I is equal to I0 into e power V by eta times of Vt minus 1, where V is the voltage across the diode and eta is the constant. Eta is equal to 1 for germanium and 2 for silicon, and where Vt is thermal voltage, that is T by 11,600. So otherwise it is represented by Kt by Q, or otherwise this is T by 11,600. So that is where T is the temperature in kelvins. So that is the reason. Then we need to convert, the given temperature is 25 degrees centigrade. So here I converted into kelvins, 25 plus 273 by 11,600, and it gives out 25.68 millivolts. Means the Vt is 25.68 millivolts. Now we can substitute this Vt value and the Vi0, then we can determine the I current. So hence I is equal to I0 into e power V by eta times of Vt minus 1. Just substitute this one, where I0 value is 25 microamperes, 25 to 10 to the power minus 6 e to the power of V. They given that 0.2 volts, and eta is I assume that 1 here, 1 into 25.68 into 10 to the power of minus 3. Then this is minus 1. Then it gives the current I is equal to 60.2 milliamperes. Then from this, we need to calculate this DC resistance and AC resistance. So if you want to identify the DC resistance, RF is defined by the ratio of V voltage to the I. So we know that the voltage is 0.2, I we got now that is 60.02 milliamperes. Hence, I substitute this V value is 0.2, I value is 60.2 to the power minus 3. Then it gives the static DC resistance or static resistance is 3.33 ohm. Similarly, if you want to calculate the AC resistance is defined as a small RF and it is eta times of Vt by I. So we consider their eta equal to 1, we observe that Vt is equal to 25.8 millivolts and the I value is 60.2 into 10 to the power of minus 3. Just you can substitute this one, then it gives that a AC resistance, that is small RF, is 0.42 volts. Now we'll see another question. The reverse saturation current of silicon PN junction diode at an operating temperature of 27 degrees centigrade is 50 nanoamperes. Compute the forward and reverse dynamic resistances of the diode for applied voltages 0.8 volts and minus 0.4 volts respectively. So here, then in this problem they given that the reverse saturation current means I0 they given. So I0 is 50 into 10 to the power of minus 9 amperes, and the given temperature is 27 degrees centigrade. First we need to convert this temperature in kelvins. So if you want to convert temperature Kelvin, we need to add 27 with a 273, then it becomes 300 kelvins. Now we need to calculate by using this formula. Vt is equal to T by 11,600. Just substitute the T value is 300 by 11,600. Then we will observe the Vt value here. Then we need to calculate this forward and reverse dynamic resistances. So we know that what is the dynamic resistances. So here from that we need to calculate. So means we need to calculate the dynamic resistances. Means small rf is equal to eta times of Vt by I. Then assume for this case the given diode is a silicon. So hence eta value we need to consider 2. So then Vt can substitute the Vt value here. And I means first we need to calculate the I. How to calculate the I? I is equal to I naught into e power V by eta times of Vt minus 1. So here you substitute this I naught value, and the V value is for the forward case V value. So for a forward case we need to calculate the V is equal to 0.8 volts, and for a reverse case we need to assume that is minus 0.4 volts. So hence here substitute 0.8 by eta is a 2 into Vt value you can substitute. Then first you observe this I value, then you can substitute this I value into this one. Yeah. So like this you should calculate this forward dynamic resistance. So similarly in the reverse dynamic resistance you should substitute in the place of V, you substitute the V value is minus 0.4. Then first you observe the I, then that should be substituted into this formula to identify the dynamic reverse resistance. Now another problem is a half-wave rectifier is used to supply 24 volts DC to a resistive load of 500 ohms, and the diode has the forward resistance of 50 ohms. Calculate the maximum value of the AC voltage required at the input. So for this given, they given that the load resistance is 500 ohms and the diode forward resistance is 50 ohms. Then we need to calculate the maximum value is required for this input. So for this case, first we need to calculate the average value of the load current. IDC is equal to VDC by RL. So for this case, the VDC value in a problem statement they given that it is used to supply a 24 volts DC, means the VDC value is they given that 24. So hence you substitute here. The VDC value is 24 volts and the load resistance is a 500. Then it gives the first IDC value. So hence first to determine this IDC value is 48 milliamperes. Now again, now we need to calculate the maximum load current. So that maximum load current is defined as pi times of IDC. So hence previously we observed this IDC value 48 milliamperes. Hence you substitute this Im is equal to pi into 48 milliamperes. Then it gives the maximum current that is equal to 150.8 milliamperes. Now after that, then we need to calculate how much maximum AC voltage is required at the input based on this given condition. So we need to calculate the maximum voltage Vm, that is equal to Im into R. R is likely V is equal to I into R. So here we are going to calculate the maximum peak voltage. Hence I consider the maximum peak current along with the given resistances. So here we need to consider the diode resistance as well as load resistance. So in this problem, they given that the diode resistance is 50 ohms and load resistance is 500 ohms. So hence you substitute this one. Im value is so 150. Just now we observed this. Previously we observed this Im value that is 150.8 milliamperes. Hence, so here you should substitute Im value is 150.8 milliamperes along with the diode forward resistance is 50 plus RL is a 500, hence it becomes 550. Then to simplify this one, it gives the maximum Vm voltage is 82.94 volts. Now another question, a full wave rectifier has a center type of transformer. So it contains, means center type of transformer contains means two secondary windings. So means the first secondary winding is 100 volts and the secondary winding is 100 volts. Each one of the diode is rated at the maximum current is 400 milliamperes. Neglecting the voltage drop across the diodes, Then solve the DC output voltage, DC load current, and peak inverse voltage of each diode. So for this case, if you want to calculate this DC output voltage, and based on that, the maximum value of the current flowing through the diode for normal operation should not be exceed. So based on that, and they in a given problem, they given that the I maximum is 400 milliamperes. Hence, the maximum I maximum should be 80% of given effort. So hence, so 80% means 80 into 400 divided by 100. That is nothing but I written like this: 0.8 into 400. That is equal to 320 milliamperes. So from that, the maximum current should be 320 milliamperes. So from that, I'm going to calculate the maximum VM voltage. So we know that so VM is root 2 times of VRMS, or we know that VRMS is equal to V1 by root 2 times of VM. So hence from this I calculated this VM is equal to root 2 times of VRMS. So in the problem statement, they given that the secondary transformer winding outputs are 100 to 100 volts, means this is the secondary AC rating, that is nothing but the VRMS voltage. Hence, I calculate this one root 2 into 100, that gives that VM is equal to 141.4 volts. Then we need to calculate how much load resistor is required. So RL is equal to VM by I max. So VM value is 141.4 by RL is 320 into 10 to the I maximum is 320 into 10 power minus 3. Then it gives that 440 ohms. Now again, in the second case, we need to calculate the DC output voltage VDC. From the full wave rectifier, we know that VDC is equal to 2 VM by pi. So we know the 2 VM is already absorbed, that is 141.4 by pi value, that gives that 90 volts. Similarly, the DC load current, I means IDC is nothing but your VDC by RL. So VDC voltage is, we observe the 90, RL value they given that so this one is required 442 ohms, hence the current is 0.22 amperes. And we know that from the full wave rectifier, the peak inverse voltage for each diode is represented as 2 times of the given VM voltage, hence it is 282.8 volts. Another problem. A 230 volts 60 Hz voltage is applied to the primary of a 5:1 step down center tap transformer used in a full wave rectifier having a load of 900 ohms. If the diode resistance and the secondary coil resistance together has a resistance of 100 ohms. Now we need to calculate the DC voltage across the load, DC current flowing through the load, DC power delivered to the load, and rectification efficiency. We need to calculate these 4 parameters here. So in this case, first you observe what are the given specifications. They given that a 230 volts means your input is 230 volts, a 60 Hz is applied to a 5:1 step down transformer. So then, and we have the load resistance is 900 ohms. So means RL is a 900 ohms. And the diode resistance means diode forward resistance, and the secondary coil transformer resistance, that is equal to 100 ohms. By using this one, we need to calculate DC voltage across the load, DC current, DC power, and efficiency. So first I'm going to calculate. So based on that, actually, if they are given like the step 5:1 step down, now we need to calculate what is the voltage across the secondary winding. So the primary winding voltage is 230 volts. Now we need to calculate what is the secondary winding voltage. So hence, given that, so this is we represented as, so based on the given windings, we need to calculate this, how much secondary voltage will be, how much RMS voltage will be absorbed across the secondary winding based on the number of turns. So in a problem, they mentioned that the step down transformer is a 5:1, means N2 ratio is 1, N1 is 5. So hence it is defined as N2 by N1, that is in terms of your given input voltage. So then it gives that 46 volts. So it is 46 volts, but we need to calculate So if you observe the center type transformer, we have the two secondary windings. So hence we need to divide again half. So for across each secondary winding. So that is the reason. So first half it contains the 23 volts and second half it contains another 23 volts. So hence it is represented as each secondary winding can produce 23 volts VI. So from this, now we need to calculate how much peak voltage will be generated. So that should be represented as Vm is equal to root 2 into 23. So we know that Vrms is equal to 1 by root 2 times of Vm. Hence, now we need to calculate this Vm. So that is the reason Vm is defined as root 2 times of Vrms. So that is 32.52 volts. So from this, now we need to calculate the VDC. From the full wave rectifier, we know that the DC voltage is represented as 2 Vm by pi hence. So Vm value just now we observe. Just substitute this one in this relation can absorb this DC voltage, that is 20.7. Then again we need to find out the DC current. So generally we know that IDC is equal to VDC by RL. So hence, so VDC by, then we need to consider that then we need to consider the diode resistances as well as a transformer secondary resistance. Hence this IDC here is represented as VDC by the total resistance is, that is transformer secondary resistance as well as diode forward resistance along with the diode load resistance. So in a given problem specification, the load resistance is given as 900. Together the source and the diode forward resistance is given as 100. Hence it is 1000. So hence IDC value is 20.7 by 1000. That becomes 20.7 milliamperes. Now we need to calculate the DC power, how much DC power is delivered. So generally we know that PDC is equal, means the power is represented as V into I, means DC power, we are going to calculate DC power, VDC into IDC. Otherwise, so V means we can write IDC by V is equal to I into R. So IDC into R means RL. Again, this is IDC. That is the reason you can also write I square DC into RL. That is the reason I shall use this one. The DC power delivered is represented as I square DC times of RL. So then I can substitute this IDC value. Then RL value is 900 ohms. Then you can absorb this. DC power is 0.386 watts. So PDC is 0.386 watts. Then we need to calculate the efficiency. To identify this efficiency, first we need to calculate the RMS value of current. So from the full wave rectifier, the RMS current is represented as 1 by root 2 times of Im. So this Im value you can also write in terms of DC current, that is 5 times of IDC by 2. So hence, so we know that this IDC value is Im value is the Im value is represented as 5 times of IDC by 2. So that is the reason I substitute this value IDC into pi by 2, and this is root 2. Then you can substitute the given values. And then you can observe this IRMS is 22.9 milliamperes. Then, so we need to calculate, means, so if you want to calculate the efficiency, then we need to calculate DC power to the AC power. So already we observed the DC power. So now I'm going to calculate this AC power. So that AC power is represented as in terms of that one I square into R, means here we are going to calculate the RMS AC current, then along with your resistances. So input side we have the diode resistance along with the load resistance. Hence, so now substitute these values to absorb this AC power, that is PAC is equal to 0.52 watts. So then we observe the DC power as well as the AC power. Now we need to calculate the efficiency of an rectifier is defined as it is a ratio of DC power to the AC power. So we observe the DC power as well as the AC power. Just substitute these two values to observe the efficiency. So DC power is 0.386 watts and AC power is 0.52 watts. Then can that is equal to eta value is 74.2. So theoretically, for a full wave rectifier, we know that efficiency is 80.6, so 81.2. So this is nearer to the this one. So hence no problem. Now another question is, show a diode clipping circuit to convert 1 kilohertz sine wave of 20 volts peak to peak to a symmetric square wave of 4 volt peak to peak amplitude. So a diode clipping circuit to convert 1 kilohertz sine wave of 20 volts peak to peak to a symmetric square wave of 4 volt peak to peak amplitude means we need to design a clipping circuit. The clipping circuit is allows the input signal is 1 kilohertz sine wave. The amplitude of the given input signal is 20 volts peak to peak means the total maximum voltage is 20 volts. Then we need to show a symmetric square wave. So means T on is equal to T off, and that symmetric square wave contains a 4 volts peak to peak amplitude. So hence just we need to show a circuit. So that is the reason we are applying the diode clipping circuits. So it contains means let us take this is your given input signal, and the given input signal the frequencies are 1 kilohertz, and this is the 1 kilohertz means the time period is 1 millisecond, and the amplitude is 10 volts positive peak and 10 volts negative peak. Hence, the total amplitude of the given symmetrical wave is 20 volts peak to peak. Then, this is sine. Then, so now we need to attenuate means, so for a given this input signal, we need to allow up to only the 2 volts in the positive peak as well as the negative peak also we need to allow only the 2 volts. So means, so we need to show like this. So we need to show like this. So this is a expected output. This blue color line indicates the given output, and this is your input signal. So hence we need to attenuate above this 2 volt signal, and here we need to attenuate the below this 2 means from below of this minus 2 volt signal. So that is the reason we here I use the two diodes here, D1 and D2, and here let's take this is anode of the D1, and the cathode should be connected to 2 volts means as per the principle of the diode we know that. So when this D1 is on condition means, so if you want to make this conduction, D1 condition should be for the D1 your applied input voltage should be greater than or equal to 2 volts. Then only we can say that that particular diode is acts as the on state. Then, so otherwise that particular diode is acts as a off means again when it is coming to your D2. So at the anode side we are having this is minus 2 volts means your D2 case your applied input voltage should be less than of minus 2 volts. Then only your diode becomes on state. D2 is becomes your on state. So let us consider if input is passing to 0 to 2 volts. If the input is passing to 0 to 2 volts, then what is the output here? So means up to 0 to 2 volts means if the V is greater than 2 volts, then we can say that D1 is on. So up to the 2 volts, D1 is not conducting means it is off state. So when your VI is less than of 2 volts, VI is less than of 2 volts. So what happens if less than of 2 volts means D1 is acts as the off state. D1 is acts as the off state, and here this is again this is 2 volts, but this is minus 2 volts. So means more voltage across the cathode. Hence D2 is also enters into the off state. Means these two diodes at this point these two diodes are replaced with the open circuit. If the two diodes are open circuit, thus V0 is proportional to VI signal. So hence this V0 here it is proportional to Vi. So means linearly changes up to this point. Yeah. Then if Vi is greater than of 2 volts, if Vi is greater than 2 volts, so what happens? If Vi is greater than 2 volts means, so more than 2 volts is passing through the D1 of anode, hence D1 is actually on state. But again, if the more positive voltage across the cathode compared with anode, D2 is actually off state. So in this condition, now whatever this is, your D2 should be replaced with the open circuit, D1 is replaced with the short circuit. So means now we are going to measure the output voltage across the short circuit path. Hence, the V0 is approximately equal to constant. That is equal to constant. This is short circuit here. So if it is short circuit, here now where this is the open circuit. Hence, V0 is exactly equal to 2 volts. So approximately equal to 2 volts. So that is the reason. When if the Vi is greater, this is up from this point to this point. This region is Vi is greater than 2 volts. At this point, the output voltage is constant to DC voltage. And again at this point, what happens up to 2 volts, then again V0 is a Vi. I'll see what happens when the Vi is, if Vi is less than of minus 2 volts. So let us consider if the Vi is less than minus 2 volts. So now we are asking this is minus 2 volts and here this is less than of minus 2 volts. So mean this is condition I'm representing. This is a minus 2 volts. So what happens here, the D1, so means the negative, more negative voltage is passing through the anode of this one. Hence D1 becomes off state and the D2 becomes on state. If a D2 is on, now we are going to measure the output voltage across the short circuit path along with the reference voltage. So at this point, in this condition, V0 is always represented as minus 2 volts. Hence, and this is Vi is less than or minus 2 volts. At this point, the output voltage across clipper circuit is minus 2 volts constant. So hence, so that is the reason. This circuit to produce a peak voltage. So now what is the peak output? This is plus 2 volts and that is minus 2 volts. The total output of magnitude is 4 volts. So that is the reason. This circuit is converts 1 kHz 20 volts peak to peak signal to a symmetrical square wave and that contains a magnitude of 4 volts. We'll see another problem. A waveform rectifier having a resistive load of 1000 ohms rectifies an alternating voltage of 325 peak volts and the diode has a forward resistance of 100 ohms. Calculate peak, average and RMS values of current, DC power output, AC power and efficiency of the rectifier. So now we need to calculate for the given problem. We need to identify the peak and average. Peak means the maximum IM and the average. I average means that is nothing but IRMS values of current. Then we need to calculate the DC power and the AC power. Then based on this DC power and AC power, we need to identify the efficiency of the rectifier. So first I'm going to calculate the peak current means IM, that is IM is equal to V by R. Hence VM by R means total resistance. Here I consider the diode forward resistance as well as the load resistance and substitute the given specifications to observe this IM value. And again first we need to calculate the average current, that is average current nothing but the IDC value. So this is the half-wave rectifier. So based on the half-wave rectifier, if you recall the analysis of the half-wave rectifier, the DC current is represented as 1 by pi times of IM. So hence is represented as 295.45 into 10 to the power minus 3 by 5. So already we observed this IM value, just substitute the IM value here and substitute the pi value, then to observe the IDC value, that is 94.04 milliampere. Then we need to calculate the RMS current or AC current, that is 1 by 2 times of IM. So that is IM value just now we observed. Then it gives that IRMS value is 147.7 milliamperes. Then we need to calculate the DC power. Already we observed this one, I square DC into RL. So already we observed the IDC value. Substitute the IDC value, then RL value, to observe the PDC value, DC power. Then the DC power is 8.845 watts. Then we need to calculate the AC power. The AC power is represented as I square RMS into RF plus RL. So already we observe this RMS value or AC current. Then you can substitute this RMS value. Then to observe this AC power is 24 watts. Now calculate the efficiency is defined as DC power to the AC power. So substitute the DC power and AC power. Then to observe this efficiency is 36.85. In half wave rectifier, we know that the efficiency is only 40.6. But this is a theoretical analysis of efficiency of the half wave rectifier. Now, in the part B, we have some questions like outline the VA characteristics of PN junction diode for forward bias as well as the reverse bias applied bias voltages, and present the static and dynamic resistance of the diode in the characteristics. So for this case, first you explain the characteristics of the PN junction diode under the forward bias as well as the reverse bias. So means that just like this is a PN junction diode. First you analyze this operation by applying the forward bias, means a P-type is connected to P-type is connected to positive pole of the battery, N-type is connected to negative pole of the battery. Then you can observe the characteristic. So we know that under the forward bias, diode is acts as a conducting state. Hence, the forward bias characteristics are drawn between VF versus IF here. So hence, your applied input voltage is increases. What happens here after your input voltage just crosses the current voltage, the current is linearly exponentially increases. And let's take this is the V gamma, where V gamma is either 0.7 or 0.3. This is for silicon and this is for germanium. Then we need to apply the reverse bias, means so P is connected to negative pole of the battery and N is connected to positive pole of the battery. Then what happens under this reverse bias, means we are drawing the reverse bias characteristic. The voltage is represented as VR and the current is represented as IR. As per the rules, as per the operation of the PN junction diode under the reverse bias, there is no conduction flows across the PN junction diode. Hence, it has very small leakage current that is represented as a reverse saturation current INR. So hence to plot, first we explain the operation for this PN junction diode forward bias and explain the operation for reverse bias, then plot the characteristics. Then in this, we need to define the static and dynamic resistance. To identify the static resistance, first define the Q point, means locate at one point in a characteristic curve. So this point intersects the two parameters, that is IF and VF, and that indicates the static resistance, that is RF is equal to VF by IF. Then if you want to define the dynamic resistance, then one draw the tangent line, it intersects the two coordinates, means so we have the four parameters here. To the rate of change of means this dynamic resistance is represented the rate of change of voltage to the rate of change of current, delta VF by delta IF, or this is also represented as theta times of VT by I. Now contrast the static and dynamic resistance of PN diode and derive its dynamic resistance. So generally we know that static resistance is defined as at any constant location, means at any particular operating point, it is defined as it is the ratio of input voltage to the means the voltage across the diode to the current across the diode. So similarly we need to calculate the dynamic resistance. So what is the dynamic resistance? Small r, it is represented small rf. So here this is defined as the rate of change of voltage. It is defined to the rate of change of diode forward current. So hence it is defined as dou Vf by dou If. Then to derive derivation means we need to define this derive, that is equal to eta times of Vt by I. Just to refer that diode resistances video to derive this expression. and explain the following terms for a PN diode, load line as well as diode switching times. So here first we need to explain the load line. So what is the importance of the load line? This load line can be used to identify the proper operating point for a PN junction diode. So under the options of given AC signal. So hence first you find out the two coordinates of a given characteristics. First hence you take the diode forward characteristic VF and IF. Then first plot the characteristics. Then you can assume that, so we know that when V in is a zero, when V in is zero, so then it offers the maximum. So then from this to identify two coordinates, so means when it offers the maximum current, that is V in by R, and when it offers the maximum diode voltage, then draw these two coordinates, and these two coordinates it indicates that a load line, and it intersects at one point. This point is called as the Q point here. Now, similar to that, we need to identify the diode switching time. So here we need to identify, means diode switching time means the how much time duration is required to change the state from on state to off state, or a off state to on state. So we are on so means diode forward transition forward time and diode reverse time, means there is only forward switching time and a reverse switching time, and we have the transition time as well as storage time. We should define here. So what is the diode forward time, and what is the diode reverse time, and what is the diode transition time, and what is the diode storage time. And demonstrate the working of half-wave rectifier with a circuit diagram and waveforms. So in this question, you should explain what is the principle of half-wave rectifier. For this case, first you draw the half-wave rectifiers. So main by using the transformer, a step-down transformer. Then half-wave rectifier uses only one diode, and it uses across the load resistance. Now we are going to observe the V0. Here this is a VN, that is 230 volts, 50 Hz frequency. Now identify here. So with waveforms means you consider the input signal, and this is the input signal Vi. Then you can explain what happens with respect to this positive peak and negative peak based on the utilization of the diode in a circuit. So we know that when a positive peak is going, then diode is acts as a conducting state, hence it allows the maximum voltage through the load resistance. So hence the maximum current flowing through the load resistance when a positive peak is passing through the signal. And similarly, what happens when the negative peak signal is passing through diode? So here D1 is acts as the off state, hence there is no flow of current across the load resistance, and the state is represented as off state. So at this point, the D1 is on state, and at this point, the D1 is off state. So like this, you can explain this operation with a waveform. And explain the working of two-level diode clippers with a circuit diagram and waveform. So two-level clippers means, so actually the clipper can be used to attenuate some portion of the given arbitrary waveform, either in the positive portion or a negative portion. So in this case, the two-level clipper means we are attenuating the portions as well as the positive peak as well as your negative peak. Means for this case, let us consider, we should draw this signal, and you can apply this one. So this is the circuit diagram for two-level clipper. You can apply the V in R, then taken this V0, D1 and the D2. So first you draw this operation, then take the input waveform. Let us consider this is the given input signal, and this is, let's take V reference 1, this is V reference 2, and you represent the reference voltages. Let us take this is my V reference 1, and let us take this is my V reference 2. Now analyze the circuit operation when Vi is less than of V reference 1, and what happens when Vi is greater than of V reference 1, and similarly you can verify that when Vi is less than of V reference 2, and similarly can identify your input is lies between V reference 1 to V reference 2, So means so for all these conditions, you should explain the operation of this clipper, then draw the expected output waveform that indicates that working of two-level diode clippers. So if you want, you can refer the clippers concept video. Now interpret the clamping circuit theorem. So here the clamping circuit theorem states that for any steady state condition, it is defined as the area under the forward direction to the area under the reverse direction is equal to the forward resistance to the R. So in this case, the clamping circuit means it says that AF by AR is equal to RF by R. So now we need to show the statement. So first you define the statement, then you can prove the mathematical theorem. So if you want to refer, then you can refer the clamping circuit theorem video. Then so first we need to define the statement. Then after that you can derive this expression. So means in this case, if I have like this, so this is the area under the forward direction. This is the area under the reverse direction. This area under the forward direction to the area under the reverse direction, that is equal to diode forward resistance and diode. This is the resistance. So illustrate the positive clamper circuit operation with a neat sketch. So here, so means we need to first you should draw the clamping circuit, and means let's take this is a resistor. Then so for this case, the input is passing through the capacitor, and let us take this is first to clamper means negative peak. Then you can apply the V in. This is the capacitor, and here we are going to take this V. Now draw this clamper circuit. Now let's assume the input signal. This is Vi. Now let's take what happens if the Vi is greater than 0 volts, and you can explain again what happens when Vi is less than 0 volts. And with respect to these two conditions, you should draw the output waveforms. So if you want to refer, then you can refer the clamping circuit operation video. Now illustrate the working principle of negative clipper with neat circuit diagram here. So for this case, means first you draw the negative peak clipper circuit. So means this is negative peak clipper circuit. So here we're going to observe, and now can, so here what happens, negative peak clipper means, so your anode is connected to ground, means whenever Vi is less than of 0, then here the diode is acts as the on state. If Vi is greater than 0, the diode is acts as your off state. So based on that, so let us consider the given input signal here. Let us say this is Vi, and now based on that, so if Vi is greater than 0, diode is on, means if ideally we taken as the ideal voltage or cutting voltage of the diode is 0, means V0 is also becomes your 0. So at this point D is on, that is the reason the ideal voltage of the diode is 0. I consider that V0 is also 0. Or practically it is equal to a cut-in voltage, and that is either 0.7 or 0.3 volts. Similarly, when Vi is less than 0, diode is becomes to off state. So here the diode is off state. Hence, if the diode is off, it is replaced with the open circuit. Hence, V0 is directly proportional to Vi. So hence, the V0 is directly proportional to Vi. Definitely. So here actually, sorry, Vi is less than 0 means this is Vi is less than 0. So this is the condition is Vi is less than 0. So if the Vi is less than 0, diode is on. So at this point, means during the negative off cycle, diode is acts as your on state. If it is on state, and we know that the voltage across the short circuit path is 0. Hence, the output voltage for this one is 0. And this one is Vi is greater than 0. At this point, the Vi is greater than 0, and here the diode state is represented as off. Hence, if V0 is proportional to Vi. So that is the reason. The V0 is Proportional to VA means linearly. V naught is also linearly changes with respect to your given input signal. So that is the reason. So from this response, we observe that the negative portion of the given arbitrary signal is attenuated or clipped. So hence, this type of circuit acts as a negative clipper circuit. Now, list the types of shunt clippers and explain the operation with the help of the transfer characteristics. Means in this question, first you identify what are the shunt clippers here. So means we are having the positive peak clippers and the negative peak clippers with these are the two conditions with zero reference voltage, and again the positive peak clipper with positive reference voltage, and again positive peak clipper with negative reference voltage. Similarly, we have this negative peak clipper with positive reference voltage. Again, we have negative peak clipper with negative reference voltage. So these are the classifications. Now we can take individually. For individual circuit, first you draw the circuit, then explain the operation and draw the transfer characteristics. So if you want to in detail discussion, you can refer the videos of shunt clippers operations. So in for the PN diode as switch and list the switching timings. So for this question, first we need to explain how this PN diode is acts as a switch. So generally we know that when the PN diode is connected in the forward bias, it allows the maximum conduction. It's under this forward bias, the diode is replaced with the short circuit and the state is represented as on state. When a reverse voltage is passing through the PN diode, then we can say the diode is acts as a reverse bias. Under this reverse bias, there is no flow of conduction across the diode. Hence, the state is represented as open circuit. That means diode is replaced with open circuit. The state is represented as off state. So under these two assumptions, here the diode simply acts as a switch. So for this case, we need to identify that how the diode is changing the state from one state to another state, means how it changes from on state to off state, or how it changes from off state to on state. So for this case, we are having some switching timings. So means diode forward switching and diode reverse switching and transition time and storage time. So you should explain all this with respect to the timing diagrams for this switch operation. So up to this point in this session, we observed that the question bank discussion on the module 1, that is diode applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.